In this final talk on deformed G2 instantons, I want to describe some open problems that I think are interesting and are motivated by what I've discussed so far. So I want to phrase these problems as questions. And the first question is, can you construct non-trivial dG2 instantons on manifolds which have holonomy G2? You see that the ones that we've constructed, they're not on holonomy G2 manifolds. They're always on, they have Einstein metrics, but the metrics are not Ricci flat. And in particular, can you do this for compact holonomy G2 manifolds? That would be the most interesting case. Another question is, can you understand the limits of dG2 instantons? So this is important if one wants to think about the compactness theory of dG2 instantons when trying to define an enumerative invariant. So for example, if you have a sequence of dG2 instantons with some control, say on their norm or something like that, what must the limit object be? And perhaps in a slightly different frame, can one understand an adiabatic limit construction for dG2 instantons in the spirit of some of the work of Simon Donaldson on Kovalev-Lefschetz fibrations? Another question that I think is interesting is, what is the dependence of the modulo space of dG2 instantons on the underlying G2 structure? We saw that the moduli space can change. It can even change dimension as we vary the G2 structure. But we see that when the G2 structure defined the same metric, then actually, although the moduli spaces had different dimension, the Euler characteristics were the same. So one could ask, potentially, maybe the Euler characteristic is independent in some sense on the isometry class of G2 structures. This is a possibility. It's not clear whether it's true or false. And in general, one needs to understand how the space of dG2 instantons changes under a variation in a path of G2 structures. Another question, again related to the enumerative invariant problem, is can one do a mirror count, where one tries to count the mirror objects, so the calibrated cycles that I mentioned in the first talk? And can one verify that the associatives with flat connections or co-associatives with ASD instantons are the same in number as the dG2 instantons? And perhaps one needs to make some restrictions to see whether this really works. And this would be some version of a kind of mirror symmetry phenomena for G2 manifolds or G2 geometry more generally. I'm particularly intrigued by the Chern-Simons functional, and I liked that we could use it to study the deformation theory. And I'm wondering whether there is a way to apply the Chern-Simons functional more generally to study deformation theory, and perhaps to study compactness. For example, we saw that in examples we had a local maximum was being defined. The f was always bounded above. Could you use the fact that f has an upper bound to say something about the compactness theory? Does f have to be bounded above? These are things that I think are worth studying. And finally, perhaps the most obvious question is, can you do all of this in dimension 8? So a spin 7 version of the things I have been saying. And one can ask a spin 7 version of all of the questions I've asked today. There certainly is a notion of deformed spin 7 instantons. And then the question is, can you construct them and can you study their theory, with a view to hopefully defining enumerative invariants? So I think in conclusion that there are lots of very interesting questions. We've only just started to scratch the surface of the study of dG2 instantons, and I hope you have found this sequence of talks informative and it inspires you to think about these very special connections in 7 dimensions.